I'm here with several members from the Faculty of Applied Science who are going to share with you their amazing research and just some of the ways engineers are making an impact in our world. This research is very often interdisciplinary, meaning from different people from different engineering disciplines or different faculties like science and medicine all work together. Many of your professors in university will be research faculty, and that means that they spend time in the classroom teaching you, as well as doing research like publishing journal papers and working to solve the problems that we face in the world every day. They're taking what they learn in their research and applying it when they teach your class. Hopefully, these very short introductions to just some of the research happening in our faculty will give you better insight into the variety of topics a degree in engineering may allow you to explore. Engineering research and the application of this research is truly changing our world for the better. So with that, I'll invite our first research spotlight to the stage. And at the end, you'll be able to use the Q&A in the stage to ask some questions to our researchers here today. All right, Trevor, go ahead.
All right. Well, thank you for giving me the opportunity to speak with you today. I'm excited to talk and reach out to every one of you here. As my name is Trevor Carey, and I'm an assistant professor here at UBC in the Civil Engineering Department. And my work, looking at kind of human health, I am an earthquake engineer, and so trying to prevent earthquake damage to our communities here in BC, but then also internationally. This is a map here of the earthquakes in the last 23 years since the year 2000 with a magnitude 6 or larger. Earthquake magnitude is just a way that we look at kind of what's the energy released during an earthquake. And as we get larger and larger magnitudes, we get more and more energy released. So in this plot, you can see there's several different colors here. They're color coded there in the lower left-hand corner with the magnitude range. But generally, as you can see, as we go up in magnitude, we have fewer and fewer events. But if we look at this kind of comparison figure, we have much, much more energy released. And so this shows you some of the earthquakes that we've had in the last 23 years just around the world. And they affect communities not just here, but also in these different regions. Just notably in this last year, we've had some really large earthquake in Morocco, just this last week in Afghanistan, and the February earthquake in Turkey. So my work is primarily trying to say, hey, we're going to have these earthquakes, but let's try to mitigate and prevent some of this damage. More closely to home, so if we think about BC here as where we're at here in Vancouver at UBC, we've had several notable earthquakes in the last 150 years. So these earthquakes can be various in magnitudes here at the on land, but then we also have this threat of a very large magnitude offshore, and we call this the Cascadia subduction zone. This earthquake could produce a large earthquake as large as a 9.0, which would be similar to the earthquake that we saw in 2011 in Japan. So my work and a lot of work here at UBC is to try to mitigate this kind of earthquake and the effects that will have on our communities. So I just have a short little video here, if I can play it here, of what I do. So I work on what's called liquefaction, and that's just how the ground responds to an earthquake. So shown here is a little demonstration by the Illinois State Geological Survey. You can see we have a saturated sand, it's kind of wet, and then they simulate an earthquake, and you can see that building start to sink. There's a ping pong ball, and that ping pong ball starts to rise out of it. And as the video stops here, you'll have a better sense of what the challenges are. And you can see all that water. And so an earthquake actually causes this. And these are some photos, some notable damage of the last 50 years. Here in the left-hand side, we have a building that had sunk during an earthquake in Turkey in 1999. This here is a large dam face that had failed during an earthquake in the early 70s in Southern California. Certainly, we have this car that had sunk in this liquefied soil. We have these building failures, and you can see the ground has cracked in this view down here. So my work here at UBC is an integrated approach to really study earthquakes. And unfortunately, we can't just look at one singular thing when we're trying to mitigate the impact to our communities here in British Columbia and then also internationally. So we have to integrate case history data. This is where we go out after an earthquake. We look at kind of past earthquake damage. We understand if there's failures or non-failures. We learn things from both. And then we look at kind of what the actual earthquake looked like, that ground motion record. We have lab experiments, so that's a lot of work we do here at UBC. We can simulate earthquake forces on soil itself. This is nice because we can do this in a controlled setting with controlled loading conditions, and this is the basis for many of our procedures. We have large experiments. This is shown here with these figures down here on the bottom. This is so we can test complex engineering systems. This would be, think about a large dam, or if we had any kind of large structure on top of a surface that might have liquefaction. And then finally, we have numerical simulation. So we're simulating what actually happens during liquefaction. We can evaluate the factors that influence it. And this is so we can improve tools that our engineering community can use to better prepare us for these large earthquakes that are going to happen. Just to kind of go in these a little bit more in detail. So one of the case histories here, this is actually a reconnaissance mission that I was on last just about 1 year ago today in southeastern Taiwan. You can see this bridge had fallen over during an earthquake. So we went out there and we were trying to understand why this bridge failed. So this is actually the photo of the team that was out there. We took out some drones and we were doing aerial photography to kind of see kind of what's the damage and what's the extent of that. But then we were also on the ground documenting that damage to better understand what was happening. So this is the same bridge, but we're just looking at from several different views. And laboratory experiments kind of already touched on this, but we can take soil samples from beneath the ground surface that would be subjected to an earthquake. We can then take those to the lab itself. We're kind of translating those in. We can apply earthquake forces, we can simplify those and just looking at cycles of loading. So going back and forth, simulating the earthquake oscillations that we would have. And then we're trying to understand really how many oscillations and how strong those oscillations are before we reach that liquefaction. We're moving that tray of soil. How many of those oscillations will cause that building to sink? We have numerical simulations, and then kind of going from left to right here, we understand these simulations are used to kind of tell us about our experiments. We use this to look at kind of liquefaction responses over a range of input parameters. And then again, we use these for our complex systems. And this is one of our greatest tools to understand the built environment of how liquefaction occurs. So we're using these tools as well. And then finally, we have large experiments. And large experiments help us be able to capture things we may not be able to capture at the element level, and they tell us if our numerical models are correct. So one of the tools that I've worked in extensively is a geotechnical centrifuge model. You can see here we have a container of soil, and we put this on a large centrifuge, and this spins it around. Think about a gravitron at the state fair or county fair. And so this spins up, and we can able to simulate large scale problems that are the size of a soccer pitch, but in a container this size. So that enables us to model these large earthen dam structures in an easy to understand way, and then we can generate data and better understand how the soil is going to respond prior to the earthquake happening, so we can better protect our communities. Just about out of time, but certainly there's a lot of folks that help and make this work together. So in addition to my lab here, there's funding partners, and there's all sorts of people that go into a lot of these experiments. And I think that will be a theme that you see throughout these presentations. Thank you very much. And I look forward to seeing you here soon at UBC shortly, and I'll pass it back to Erin.
Well, hello, everyone. So my name is Madisyn Szypula, and I am a master's student, actually, at the UBC Okanagan. So let me go to my next slide here. So I completed my undergrad at UBCO in mechanical engineering. So I wasn't in your footprints not too long ago, only 5 years ago now. And today I'm going to be talking a little bit about my master's research, which is looking into the process of plastination to create a composite material, which I'll get more into after. And before I do that, I would actually quickly like to talk about some other research that I've been a part of. The most exciting is probably my interdisciplinary research with therapy dogs and immersive technology, specifically virtual reality and augmented reality too. So the reason I'm bringing this up is, as an engineering student, you can really branch out into a lot of different areas and use what you learn as in engineering as an asset to be able to explore some new areas. So back to my master's research, right? So plastination is a technique primarily used in biology to preserve human bodies. You may be familiar with this if you've ever been to a museum that has the Body World exhibit. I believe there's the main one happens in Amsterdam, and then there's also traveling ones all over. So basically, plastination is a method that works by getting rid of moisture and replacing that moisture with a polymer. So think of it as moisture, as in maybe we can think of it as water, and water, when it's in a cup, takes up space. So what I'm trying to do is remove that water from that space so then I'd be able to fill up the empty space with something else. So how it works and within composite materials. So my goal is to use plastination on natural materials like wood or natural fibers, which you can think, some of you might know about carbon fiber. Natural fibers is a very similar aspect, but it's a biomaterial. So what I'm trying to do is basically create a new biomaterial. So how does it work? First off, I start with trying to get rid of the moisture. So I submerge the wood in acetone, and the acetone works as a dehydration material. The next step that I do is to replace the acetone, that it has now replaced the water. I put it in a vacuum atmosphere, and this vacuum atmosphere allows the acetone to evaporate, and basically that leaves my, say, pores empty in the wood, and what happens is the polymer is then able to be sucked into the wood. Finally, after that, the polymer is liquid in the forced impregnation step. So what I have to do is I have to cure or harden the polymer. So what I do is I bake the wood in an oven. And then finally, I use X-ray tomography to create 3D representations to see how well the polymer was replaced the moisture. So you can see in the results section here, it's not a 3D slide, it's a 2D slide, but the white is the polymer that's been impregnated into the fibers of the material, and then the black is where it hasn't been. So it's still a work in process of what I'm trying to do. And then you may be asking yourself, why am I doing this? Well, wood is a natural material that rots really easily, and I'm trying to create a material that's more durable to elements in the weather. And I'm sure many of you have seen wood rotting. You've probably been on hikes, anything like that. So to kind of talk more about how this impacts human health and things like that, I am using life cycle thinking to create this new material. And basically what this means is I'm looking at all the impacts that could potentially be created by this material at every step of the process. So that means from raw material extraction all the way to the end of life, like how is this material being recycled? Can it be reused? Everything like that. And when you're using life cycle thinking, you look at impacts, and there's a whole wide range of impacts that you can look at. So there's environmental impacts, but there's also human impacts on health, on quality of life, everything like that, which you might be saying, how does wood affect quality of life? But you'd be surprised with how small things can actually add up in the end. So in the end, my goal is to create a product with the least amount of harmful impacts possible. And that's all for me. And I hope I gave you some insight on what engineering could look like for you. And I will pass it to the next person.
Hello, everyone. My name is Antony Hodgson. I'm a professor in mechanical engineering, and I run a group called the Surgical Technologies Lab that's based at Vancouver General Hospital. Thanks. There we go. So what do we do at the Surgical Technologies Lab? We basically work with surgeons who work on bone. And so these are surgeons in orthopedics, in plastic surgery, and in maxillofacial surgery. And the main goal of the work we do focuses on trying to improve the accuracy of surgical procedures, trying to lower the amount of radiation dose that's used during these procedures, to improve operating room efficiency, to think about ways of introducing automation into some of these treatment processes, and overall trying to bring down the cost of treatments so that we have the best outcome for the patient. We've got a lot of projects listed here on the left-hand side of the slide, and I'm just going to take you very quickly through some of the major categories of work that we do. So one of the main areas we work in is an area called arthroplasty, or otherwise known as joint replacement. And this is when joints like your knee or your hip or your ankle or your shoulder you have something like arthritis that causes damage, and it makes it very, very painful. So you want to have it treated. And the main treatment is to replace that with artificial joints. And this procedure is done a lot. It's done almost 500,000 times a year in the US alone. And it's generally a very good procedure, but there's still about 7% that fail, that have to be done again. We call this a revision. And so a big part of our goal is to try to figure out ways to reduce that, to prevent that from happening. Another kind of surgery that involves significant pain for the patients is spine surgery, and it's done because of chronic back pain that can be due to a variety of conditions, sometimes degenerative. And in a number of these situations, one of the main surgical tasks is to replace or to go in and insert some hardware, as shown on the right here. And it looks a little, a little machine-like. You put in bolts and screws and rods, and the purpose is to try and take the pressure off the nerves and try and keep the bone structures from impinging on that. One of the challenges surgically is how to prevent the screws, how to help the surgeon prevent putting the screws in such a place that they actually impinge on and create more nerve damage, which in a percentage of cases can lead to them having to redo the surgery. And so that's a big part of what we're trying to do. We work with trauma surgeons. So if you were unfortunate enough to be in a high-speed accident, whether it's car or motorcycle or skiing, you might end up with a fractured pelvis. And if you have a fractured pelvis, you have to do a similar kind of thing. You have to introduce a screw that bolts basically the pelvis back together again. And what we're trying to do is to avoid the situation that's shown on the right, where the screw is coming out of the bone and impinging on blood vessels and on nerves that can cause a less than desirable outcome for the patient. And so we're trying to provide surgical tools that make it possible for the surgeon to do this reliably and accurately. And another area we work in is with pediatric surgeons. So these are doctors who are treating newborns. One of the conditions that we work with is called developmental dysplasia of the hip. And this is a congenital abnormality that occurs in about 1% to 3% of babies, predominantly baby girls. And the way that we diagnose this is with ultrasound. And so one of the baby is scanned with an ultrasound probe, and it produces an image like the one shown in the middle. And doctors then try to analyze features in this image in order to decide whether to treat or not treat the baby. And the challenge is that the ultrasound scanning process is highly variable. And so we're trying to apply machine learning techniques to figure out how to automatically process these images to give them the most reliable measurements possible for developmental dysplasia. So I want to show you briefly some of the systems that our students have developed in the lab here. This is an example of a targeting tool that is being used for shoulder arthroplasty, so fixing a shoulder joint. That's a real surgeon there that we collaborate with. What you're seeing at the upper left is a stereo camera, and the interesting feature in this particular system is the special kind of QR codes that you can see on items 2 and 4. And we're measuring the relative position of the drill and the shoulder and trying to help the surgeon drill as accurately as they can. And we were measuring the accuracy of this particular system. This is a really interesting device. Maybe we can roll that first video, Erin, if that's possible. So yeah, I don't know if we can play that. Perfect. So this is a bone-mounted robot. One of my previous PhD students developed it. It's one of only a handful of robots that are in commercial development. You can go and buy this if, if you're a hospital. And what it does is it automatically positions this cutting tool in precisely the right places to make the bone cuts that are necessary to replace the joint. So now we can go back to the slide presentation and move on to the next slide here. One of my more recent students, and I guess there's another video that goes with this, one of my more recent students has been moving this technology a little bit further. And instead of just having bone cuts, what he's developed is a tool for milling the bone. And this allows us to get more curved surfaces and use what are called bone conserving implants. So implants that are designed to not require as much removal of bone and that can therefore give the patient a longer time with the implant that they get. We'll go back to the slide and show again for a moment. And so next slide then is this one. So another example is many of you will know about various augmented reality and virtual reality devices. This application was built with the first version of the Microsoft HoloLens. And what we're trying to do is to provide more natural mapping for the surgeons to use when they're performing surgeries. So in this particular example, what you can see is the surgeon is operating with their hands right down in front of them, but they're looking over at the screen that's across the patient. And what we're trying to do here is to give them a view that is more naturally mapped to the surgical scene. So if we go to the last video here, what you can see is an overlay. So this is a virtual reality scene. In the background is a real physical model of the pelvis. And what we're overlaying on this, and sorry for the this going out of scope a little bit, we're overlaying a virtual reality model, and we plan to use this to help the surgeon do targeting and also visualization of the surgical task that they're performing. So if we go back to the slide presentation, I'll just go forward now. So that's what we just saw. And I want to thank you. This is the surgical robot, the milling device that I showed you earlier. So happy to take any questions shortly.
All right. Good evening, everybody. And well, thank you. That was an excellent presentation by my colleague, Tony Hodgson. I too am a member of the School of Biomedical Engineering, and I am a chemical and biological engineer by training. And today I'll like to talk to you a bit about a couple of projects where we have had tremendous impact, not just in health, but also looking at human impacts on climate and the planet. So let's start with the most recent example that the world has been through, which has been the COVID pandemic. The race to develop and deliver vaccines to every single citizen on the planet has truly been one of the wonders of modern science and technology. And a core part in the production of these vaccines has been bioprocessing and biomanufacturing. And so in my research group at UBC, we spend a lot of time on developing improved biomanufacturing processes. These processes can produce different products. They're more efficient. They produce products more cheaply and more efficiently. And most importantly, they are producing safe products. And as part of that, a key piece in biomanufacturing is a process called fermentation. Most of us are familiar with fermentation as the operation that is used to produce fermented foods, such as beer. But fermentation is a critical operation that is also used to produce drugs and vaccines. And the technology that we have developed in collaboration with Sanofi, which is a large pharmaceutical company, is to develop a new recipe for a process called cell-free production. And the philosophical origins of cell-free production is if I am having a microorganism that is growing in a fermenter and I give it its feedstocks, carbon and nitrogen, the microorganism will produce more cells of microorganisms and also produce the product of interest. Now, that process, the product of interest is your primary product. more cells is an unwanted byproduct. And how does one apply engineering to produce more of your drug and less of the cells, thereby making the process more efficient? And this is precisely what cell-free protein synthesis is able to achieve. So if you have to simply visualize this process, take the microorganism, and rather than the microorganism producing more of its cells, what if we could take out the machinery from inside the cell and use that machinery, which is extremely efficient, to produce the protein of interest? And what is guiding that machinery is a piece of engineered DNA. And you take this entire vision together, and what you end up doing is getting a more efficient route to produce product on a substrate-fed basis. And this is precisely what we have done with Sanofi, our pharmaceutical industry partners. And we have put this technology to good use to produce certain vaccines that are already in clinical development. So the example that we have done is to look at the pertussis vaccine. So we are looking at the fimbrial protein on the B. pertussis strain. And the systems that we have developed, when you compare it to existing systems, they are roughly 7-fold cheaper and 2.5 times more productive. And this has been a game changer. And Sanofi is now using these processes for the production of the next generation of flu vaccines. In terms of what else can we produce using cell-free systems, I have mentioned proteins. You can also produce DNA and mRNA, and this is precisely where some of the next generation mRNA vaccines are being produced. And similarly, we can also produce certain neutralizing antibodies that can be used as therapeutics for COVID-19, for instance. And to give you a complete summary of how we have married different aspects of engineering, we have actually gone one step further and developed a completely streamlined process to rapidly develop new therapeutics. So in the instance, we are using rapid prototyping to come up with new reactor configurations. These reactors are then used to test different manufacturing strategies. We are incorporating microelectronics for sensing and monitoring these processes so that it gives us real-time information about safety and quality of the product. And eventually, we are bringing biochemical engineering, industrial engineering, as well as electrical engineering. And these are processes that are already deployed and running in the industry as we speak. And the idea there is using this to drive the next generation of manufacturing processes. And very briefly, in order so that we have some more time for Q&A, we are also looking at a completely different sector, which is mining. And my lab has been able to develop a technology which we eventually spun off into a startup company, and that is addressing the challenge of acid rock drainage. And so not only are we looking directly at human health, but we are also looking at the impact of climate and pollution on human health. And the idea there is the company is called Tersa. This is the company that has now commercialized this process. This came from a very innovative idea in the laboratory. And essentially, the way this process works out, I'll show you a schematic. We have developed these water treatment systems that are now being deployed at mines around the world. And this is able to treat mine-impacted water. It is able to pull out useful metals and also reduce the carbon footprint of these operations. So with that, thank you for your attention, and I will revert back to Erin and the rest of my team. Thank you.
Perfect. Thank you so much. So I am going to pull everyone back on stage. We have a few questions that were submitted. Perfect. We have everyone back on stage. So there was a question for Trevor. This is a very long question. Maybe you can summarize it as best you can. So the question is, how accurately can lab experience represent real life conditions during earthquakes? Could you talk about some of the challenges you faced and ways you adapted the experience to become more representative of the real world? And what tools and technology has been available at UBC that helped you achieve this?
Yeah, so any lab experiments that, and you'll probably get this from everyone on this call, we're trying to represent the real world as best as possible, and that's why we do it in the lab. We're trying to recreate some kind of conditions, and so with our earthquake engineering concepts and what we're doing in the lab, we're trying to best as we can represent what we would see during an earthquake. So we're doing the best we can to kind of be as true to that process as possible. But that's also why I kind of showed you that circle diagram where we're integrating several different tools. So we know that one thing can't do every single thing, and so we start to build in other aspects to kind of support and augment that. To the second point of kind of, I have the questions down here. So the challenges that we face, I think one of the challenges is just you have to have the creativity to kind of say, hey, what are we trying to measure? And then can we measure that? And so that's kind of working with some of the UBC, the folks that are here at UBC to help machine this, or looking at the equipment that you have. I think here at UBC, in the civil engineering department, we have a large shake table, we have well-stocked labs, we have a machine shop that can really help us to achieve some of the goals that we're trying to do with these experiments. And then I think one thing, not necessarily technology, but there's a really strong community of researchers that are really active, wanting to address these problems. So you can always bounce ideas off of them and work with them to better understand and kind of better integrate these ideas in your experiment. And it's always great to get a diverse set of opinions and a diverse set of ideas when you're trying to address these complex problems.
Awesome, thank you. Another question that anyone can chime into, but there's a question for all of you who are professors. Do you find that students engage well in lectures and ask good questions? Are they often curious, outspoken, and showing passion in your classes? So maybe you can kind of address what that experience is like at UBC. Anyone that wants to answer.
Maybe I can bite the bullet there. So the answer is 100%. In fact, I guess I can speak for all my colleagues at UBC. The greatest single motivator that gets me to campus every day are the students and the engagements that we have with them. It's their enthusiasm, their curiosity. They really want to change the world and in a positive way. And that's what actually motivates me to come. So, it actually is a different type of motivation. And so they are phenomenally talented. And the advice is to always remain curious and to remain committed. That's going to be essential for success.
Awesome. Thank you. Maybe one last question before we wrap it up today. So there was a question about, do undergraduate students ever get to do design work and research like this, or is it only for master's, PhD students and researchers? So Madisyn, I don't know if you're involved in any research in your undergrad at all, or if anyone works with undergrad students that would like to mention anything.
Mm-hmm. I did partake in research as an undergrad. So I did it both within engineering and outside engineering. So 100% those opportunities are there for you. My biggest thing is get to know your professors, because they're more likely to let you into their labs if you have a good rapport with them. So yeah, 100% you get to do stuff. And design work as well. In your final year, you do a capstone project, takes up the whole year. So you definitely get to do a lot of stuff.
Yeah, and I can add a couple of things. So I think there are two main ways that you can participate in research. One is during the summers, and you can do that pretty early in your time at UBC. The National Funding Agency actually has a program where you can apply for scholarships and you get paid to work. It's essentially a summer job that often qualifies under the co-op programs, so you can get co-op experience doing that. Most programs also have a fourth year research project where you get course credit for it, and so you can work one term or both terms on a research project. So a lot of students will do that as well. And I would be remiss if I didn't mention that there are many design teams, student design teams, that are not necessarily attached to any research labs, but students are coming together in groups, small and large, to deal with all sorts of challenges. They can be in the area of, I think civil engineering has the concrete toboggan race, and there are robotics teams, and there are space teams, and there's the biomedical engineering student team that takes on all sorts of challenges. So many opportunities to participate in design and research at the undergraduate level.
Wonderful. Thank you all so much for joining. It was really great to hear from all of you. I learned so much. I always learn so much, and I find it so exciting. So I'm always excited to learn a little bit more of what everyone is doing and researching and how you're all making the world a better place. So thank you all for being here. I'm going to take everyone off the screen. We'll be back in just a couple of minutes with our admissions presentation. I know you're all looking forward to that. So I'll take you all off the screen. We'll be back in just a second.